SEC. He's responsible for designing, developing, and demonstrating the world's most advanced centrifuge for uranium enrichment. Bob has over 40 years of experience in the nuclear fuel industry and holds 3 patents in the field. Bob?
Thank you. USEC is licensed for 10%. If there's a market, I'm sure we can look and see how.
What sets the Russians your phone number?
Phil talked about that he went sort of a mile wide and an inch and a half deep. I'm going to do 5 miles wide and about a half an inch deep. So, and I sit here and I look at this, and when Shirley asked me to talk about the fuel cycle, you know, back in my previous life I was involved in it pretty heavily, but it's been probably 15 years. And as well, really hasn't changed that much. But I look at some of the people here in the audience, I think you could teach me some things. So just bear with me. It's about enrichment. I can answer pretty much any question, but when it comes to the fuel cycle, I'll give you my best. So basically what I'll do is I'll just go through an overview of what the fuel cycle is. We've talked about the SMRs. We're going to be talking about that later today. Obviously, you have to have fuel to get it in. You've got to have enrichment. You've got to be able to fabricate it. And then you've got to decide what you're going to do with the material when it comes out. So I'll just kind of give an overview of each one of those. This is the current nuclear fuel cycle as we know it today. You start with uranium mining and milling, taking it out of the ground. And then you convert it into a form that allows you to enrich it. It goes to the enrichment to take it up to the assays that you need to run the reactor. Then you take that and you take the fuel fabricators to convert it into an oxide and make fuels out of it as it goes into the reactor. And currently, the material that comes out of the reactor is stored. So that's the current fuel cycle. Okay. We'll go through each one of these in a lot more detail. So let's just look at uranium mining and milling when we talk about it. Basically, again, what we're talking about is how it's removed from the earth, and it comes in the form of the ore, and it's crushed and it's concentrated and made into uranium oxide. When we look at where uranium is worldwide, basically it is all over the world. More than 30 countries have uranium mines, but probably, I think only 6 countries probably mine more than 50% of material. Those are primarily in Canada, in Australia, countries in Africa, and in Russia and Kazakhstan, where there are mines that are producing material, most of the material. And we talk about that. When it comes out of the ground, the typical uranium ore will have anywhere from 0.2 to 0.3% oxide. And that then has to be converted to much higher percentages. But if you look at Cigar Lake up in Canada, their ores can go as high as 50%. A lot of them are more than 20%. So when you think about the economics, here in the U.S., our mines are primarily in Colorado and New Mexico. They're about 0.1%. So when you think about economics of mining and where you get your ore from, you got 20%, you got 0.1%. Where's the business going to come from? It's pretty simple. And that's basically the key thing about the fuel cycle. A lot of it is just basically based on economics. So how do they do the mining? Well, again, because the ores are located in different places, some are very deep, some are at the top, and you'll look at the different methods of mining. You can have strip mining for the material that's up at the top. You can have shaft mining, anything that's down 120 meters further below. New kind of mining methods they're using now are in situ mining, where they take oxygenated water and they will inject that in. Maybe put a little sulfuric acid, a little acid with it to leach out the uranium. These are different forms. There's also uranium present in the seawater. You can mine it out of seawater. It's about, I think about 400 parts per million in seawater. So uranium is everywhere. You just have to decide from economics where you want to get it and how you want to get it. This is just a picture of open pit mining. So when we talk about the mining and the milling process, Just basically standard chemical type processes. Nothing special. You have rock crushers that's going to crush it up. Slurry pumps that will pump the material around. You know, I said you use sulfuric acid or something to leach the uranium out. Probably somewhere between in a reactor that has a 1,000 megawatt reactor, you'll mine anywhere from 20,000 to 400,000 tons of ore a year to fuel that reactor. And then as it's converted to U3O8, it's typically called yellow cake. It actually has a khaki type color. Depends on the processing. It's one thing you'll see about uranium. Depends on how the material is processed, how the oxide is made, whether it's made by a diurenate process, nitric acid, calcine, whether it's just oxidized. The forms will be different, and they'll have different colors. But U3O8, which is the basic material that comes out of the mines and the mills, is called yellow cake. And it will have a yellow tint, or it'll have a khaki tint to it. So you take the material out of the mines and the mills, and you send that to be converted. The basic uranium fuel cycle in the U.S. is based on UF6, uranium hexafluoride. There are other fuel cycles. The AVLIS process, atomic vapor laser isotope separation process, which was developed back in the 80s and the 90s, was based on uranium metal. That was one of the challenges it had, was how do you integrate the uranium metal process into a UF6-based industry? Feed converters, the fuel fabricators, they're all set for UF6, and here you're trying to institute a uranium metal process. So that was one of the challenges that you had. So at the conversion plant, the oxide then is combined with fluorine gas, and it's converted usually to UF4, and then hydrofluorinated to UF6 after that. UF6 at room temperature is a solid and it's crystalline. This just shows you, again, as I was talking about before, some of the various forms of uranium oxides, uranium compounds that are used in the fuel cycle, and you can see the different colors. So these are just uranium chips, uranium metal chips. UF4, that's commonly called green salt. You hear the term green salt. And it is, it's a green salt. Then you have your yellow cake, there's U3O8. Here's a different form of U3O8 beside over here. Again, depending on how the process is made. There's UO3, UO2, UO2. The granularity, the forms are based on the processes that are made for it. And when you start making, when you go to the fuel fabricators and you're making nuclear fuel out of it, it is a very black art process. And if you go to fuel fabricators, they will not tell you exactly how their oxide is made, because the quality of that fuel depends on how long you burn it, etc. It's a very, very protected process and a black art process. So we go back to the conversion process to convert it to UF6. Again, basic chemical processes. When we talk about the nuclear fuel cycle, when we talk about the hazards of the nuclear fuel cycle, on the front end of that fuel cycle, the hazards aren't really radioactivity, very low radioactivity. The hazards are basic chemical processes, chemical production processes. So what you see here are basic processes that you see in a feed conversion plant. This is a feed conversion plant here in the U.S. It's in Metropolis, Illinois, now called Compradine Honeywell Conversion Plant. There's also one up in Cameco in Canada, or two different operational in North America. So then that gets us to the next stage, enrichment. So when the uranium comes out of the ground, it contains 0.7%, basically 0.711% of natural uranium. And to go into a reactor, you'll want to convert that up to anywhere between 3 and 5% for your basic light reactors. And originally, they were looking at 3 to 3.5%, and As the reactor companies decide they wanted longer and longer burn-ups, then it approaches closer to 5%. In fact, I think about
Hey, man, just
80%
one
of the
second.
market now is between 4.2 and 4.95% asset. And that's basically what we're showing here is 0.711, 0.72%, 235. The balance primarily is uranium-238. The 235 obviously is a fissionable isotope that's of interest. For light water reactors, it's at 3 to 5%. Submarine fuel weapons are greater than 90%. That's obviously a different plant. Concentration of U-235 natural value is called uranium enrichment. There's several different forms of ways to enrich uranium. The one that's most popular now worldwide is gas centrifuge, and I'll talk about that in more detail. The one that was most popular that has recently essentially closed throughout the world was gaseous diffusion process. Gaseous diffusion would basically take UF6 gas and feed into what's called a converter. Converter contained barrier tubes, and it was based on kinetic energy. The higher kinetic energy, the U-235 F6 versus the U-238 F6, would hit the walls of the barrier, would diffuse through the walls, and you get a slight separation factor. And the theoretical separation factor for gaseous diffusion is 1.004 molecules of 235 for every molecule of 238 that you would get. So if you want to convert that from 0.71% up to 4% enriched U-235, it would take 1,000 stages to do that. It would also use an enormous amount of power, because what you're doing is every time that you take the pressure drop across that barrier wall, you would have to repressure that up to the next stage. That was very, very power intensive. Electromagnetic isotope separation over here at Y12, largest one in the world, galeutrons. And so that was a very inefficient process, but it certainly did its job in the 1940s. I talked about the laser process. Two primary laser processes. The one I talked about before, AVLIS, atomic vapor laser isotope separation process, was based on uranium metal. Used tunable dye lasers. Those tunable dye lasers, you would tune the frequency like you would tune a radio to uranium-235, and that would excite the 235 and make that an ion, and then you would collect that as a charged particle. The other laser isotope separation process, the one that was here in the U.S., originally was called molecular laser isotope separation. Now the Australians have one very similar. It's called SILEX, selective isotope laser excitation. It was based on UF6. So they didn't have the problem of the uranium metal fuel cycle versus UF6 fuel cycle. Basically, that uses a carbon dioxide laser to convert, excite 235 versus 238. That process has a ways to go before it will be ready to be commercialized. Chemical ion exchange is a chemical process. The French and the Japanese have ion exchange processes. Aerodynamics, vector nozzle process was done in South America. Basically, it's like a centrifuge process. You have a knife blade. You accelerate the UF6 around and you get a separation to 235 versus 238. And the plasma separation process is one that was developed years ago by TRW. So these are different ways to operate, to enrich uranium. This is a photograph of the plant up in Piketon, Ohio that USEC is building, and currently we're actually operating 120 machines right now in a demonstration for the Department of Energy. One of the values that go back to the theoretical separation efficiencies of gaseous diffusion was 1.004. For centrifuge is 1.04. It's basically an order of magnitude more efficient than the gaseous diffusion process. Therefore, it uses only about 5% of the energy of gaseous diffusion process. When we look at the overall fuel cycle, when we look at the cost of fuel cycles, you you can see the bulk of the cost is in the phase that we were talking about first, the mining and milling phase. About 45% of it comes there. The 34, over a third of it comes in the enrichment phase, 15% is fabrication, and 6% is conversion. With the enrichment, the world's three world enrichers, you can see listed here. USEC, we have about 27% of the market. Eureka is a consortium of Germany, Netherlands, and the United Kingdom. They own about 26% of the market. Rosatom, Russia is about 23, Korea is about 16, and some other various forms. There's about a 48 million separate work unit. What is a separate work unit? That is the commodity that's used when we talk about enriching uranium. It tells you what is the assay and what's the total quantity. That's how enriched uranium is sold in the market. And basically, it's about a $7 million unit. Well, there I've defined a separate work unit. Basically, what it is how much work does it require to take an assay, natural assay, 0.71%, and take it to 3.5, 4.95. How much work does it take to get there at a particular given flow rate? And just kind of rule of thumb, it takes about 7 separate work units to produce 1 kilogram below enriched uranium, 4.6%, 9.4. So it's about 10 to 1. About takes 10 kilograms of uranium to end up with 1 kilogram of fuel, and it takes 7 separate units to do that. To fuel a reactor, a 1,000 megawatt reactor, every year takes about 100,000 separate work units to do that. So the plant that USEC is building is 3.8 million SWUs. So basically, that would fuel 38 reactors. Just a little bit about our plant. Our process is based on the process that was developed by the Department of Energy back in the 1980s. DOE had invested over $3 billion in that process. Since then, we've invested another $2.5 billion. How is our machine different from what the DOE developed back in the 1980s? Well, we took advantage of improved materials. Obviously, in the 1980s, we had a fiberglass rotor. We have carbon rotors now. What do carbon rotors do for you? They're lighter, spin them faster, more durable. Electronics that we used in the 1980s, certainly there's been a renaissance in electronics. We improved the electronics. The modeling capabilities. When you talk about separate work units, you want to get more SWUs per machine. Think about a $150, $120 SWU for a machine. For every SWU that you're talking about, for our plant, is 11,520 machines. For every 10 SWUs we can increase in productivity, that's worth about $20 million a year in benefits. Going back again, economics. It's all about economics. So this is how does a centrifuge machine work? Basically, again, you have a rotor, long thin rotor, that spins at high speeds, and it separates the J6 gas. And the way it does is there's two methods of separation. There's centrifugal separation. Centrifugal separation takes place in the radial direction, and you also get an axial separation. So the theoretical separation efficiency of a machine, a centrifuge machine, is based on how tall you make it. It's directly proportional to the height, and it's proportional to the velocity to the fourth power. So the faster you spin it and the taller you make it, the more separate work units you can get in a given space. And then the machines, just like in the gas diffusion process, they're coupled together in what's called a cascade. There. And so basically what you're doing is you're feeding in multiple machines in parallel arrangements, and then they make a stage in multiple stages. And that's how you go from the 0.711% up to your 4.95%. And what's left is, if you enrich product, you also will have a depleted product. And that typically is 0.25%. Again, that's dependent upon what's the cost of your feed is how low you take your completion ratios. So the cheaper feed is you put in more feed and you'll have higher assay on your tails. The more expensive the feed is, you'll use less feed and have lower assay. You'll strip what's called stripping uranium out of the tails. And you've probably heard recently about re-enriching depleted uranium, re-enriching the tails. The basic tails that there's probably over $1 billion worth of material sitting at Paducah and Piketon right now that are depleted uranium. And they contain anywhere from about 0.25, 0.2 to 0.4% uranium-235. So if you can economically strip those tails and use those, basically mine and enrich the 235 uranium out of those tails, then again, it's based on economics. If you can do that economically, then it makes sense to do that. And that the Department of Energy recently put out a request for proposal for people to re-enrich depleted uranium tails. So let's compare machines. As I said, the taller you make them, the faster you spin them, the more separate work units a year you get out. What you see here are the three primary machines that are used in the world today. The Russian machine is about 2 to 3 feet tall, and it will produce about 8 separate work units a year. The European machine, which is the French, the German, the Brits, the Dutch, and the Germans, is about 12 feet tall, and it will produce about 40 separate work units a year. The US machine is about 43 feet tall, and it produces about 350 separate work units. We've been able to, in the US, demonstrate how you can take a tall cylinder and rotate it at very high speeds and overcome some of the mechanical challenges that you have and have a reliable operational machine. Now, the Russians and the Europeans will say they've been running their machines for 30 years. They know their machines will last. They know it. In the U.S., you haven't run yours for 30 years. That's correct. We have not run our machines for 30 years. But we did have over 10 million hours of DOE machine previously, and I'll show you how many hours we have running on our machine right now. And all of our analysis and models tell us that the way machines are running right now, there's no reason they will not be 30-year life.
Well, and that's what's at Piketon?
Yes. You'll see a photograph of that. This is exactly the machines that we have operational in Piketon right now. There they are. These are actually the DOE machines. I'll show you where our machines are. If you look at the DOE machines, you look at our machines, you wouldn't tell the difference because one of the criteria we made was we wanted them to sit in the same footprint. So basically they're in the same casing, same physical footprint. That shows you. As I said, DOE built about 1,500 of those machines. They ran more than 10 million hours. Some of those machines ran over 10 years before they were shut down. Their separate capacity was 200 separate work units per year. So we're 350. Same footprint, but our efficiency because of the things we've done, we've got done at 350.
Bob? Just a question on that. Who does the seismic qualification of those banks of centrifuges? Do y'all do that at USEC?
Yes. There was actually a lot of seismic work done that was back during in the 80s, and we picked up on that, and then we extended that through our analysis. So why use the American centrifuge machine? You got the Russians and you got the Europeans. Why have an American centrifuge machine? Well, there's numerous reasons. First, one of them, security of supply. Certainly, we do not want to be in the position that we were in oil, where we're dependent upon foreign supplies for energy needs. Manufacturing. Our machines are built right here in the U.S. In fact, basic rotors are built right here in Oak Ridge, Tennessee. We have in our casings come from Indiana. Our rotor tubes come from West Virginia. Our valves come from North Carolina. Our service modules come from Alabama. We are creating over 8,000 jobs of at our plant here that are U.S. jobs. Redeveloping the U.S. technology that was lost 30 years ago. National security interests. Certainly you cannot get to the table of non-proliferation unless you have your own indigenous uranium enrichment supply capability. We found that out. More importantly, here at Y-12, the weapons facility, weapons contain tritium. You have to, tritium has a half-life of about 12.3 years. You have to modernize and refurbish those weapons on a regular basis. By treaty, the tritium is made TBA at Watts Bar. By treaty, you cannot use enriched material from a foreign supply to go to be used to support the U.S. weapons industry and go to the weapons. It has to come from a U.S. supply. The only indigenous U.S. technology is barium centrifuge. So it's very important. And I think the Department of Energy is very confident. Modular expansion. One of the beauties about this process is it's modular. So as you develop new technologies, the gas diffusion process was developed for over 60 years. The improvements were made, the efficiency of the gas diffusion plant was significantly improved over those 60 years. We're just on the beginning of the curve of how much better we can make these machines, how much lower cost we can make these machines, how much more efficient we can make these machines. And then there's the environmental benefits. Meaning 95% less electricity, 10 million tons of greenhouse emissions are saved each year. This is a photograph of our plant right now. I said we have 120 machines operating. We have an agreement, an RD&D agreement with the Department of Energy that we will demonstrate by the end of the calendar year 60 days of operation and performing at the average of 350 SWU per year, meeting a certain reliability and availability rate. And those machines are in piping. Right now we have accumulated over 143 years, 1.25 million hours of runtime on those. The clock will go down on our 60-day test the first week of October. We'll run that for 60 days, demonstrate we can do that. We'll met our RD&D agreement. That was an 18-month program that we had with the Department of Energy. We're on schedule. We're under budget. We've met every milestone DOE has put on us. ORNL, it was tasked by the Department of Energy to review our program, and they've been reviewing it on a regular basis. That's enrichment. So you got your enriched UF6. Now you got to get it in a form that you can take it to the reactors and then put it in the reactors. And that's done by the fuel fabricators. As I said, basically what you're doing is you're taking the UF6, converting it back to uranium oxide as fuel pellets, and then they're loaded in fuel bundles in place of the reactor. I'll talk a little more about that in a second. Reactors, certainly that is where the why you're doing this. You want the energy. And just let me give you a couple of numbers. 1,000 megawatt reactor, 1 ton of natural uranium will produce 44 million kilowatt hours. To do that same amount using coal would take 20,000 tons of coal, factor 20,000, or it takes 8.5 million cubic meters of natural gas. Another way to look at that is in the reactors, the fuel assemblies are fueled by fuel pellets. One pellet has the same amount of energy as 1,780 pounds of coal or 149 gallons of oil or 17,000 cubic feet of gas. So when you think about that, you can think about the efficiency and the importance of the reaction. So let's talk just briefly about reactors. You're going to hear a lot about small modular reactors. The key there obviously is you want a chain reaction, and in that chain reaction you're burning the fuel, and that's the radiation is what gives you the energy. Most reactors are thermal reactors, and they use a moderator. Basically what the moderator does is it slows the neutrons down so that you can get efficient. This shows the nuclear reactors across the world. Bill's already talked about is 435. I think he said it's 433 now or something like that. It goes up and down based on the operation. But the key thing is you can see that there's 66 now that are under construction. Most of those are in China. You see China there. They have 14 operational. They have 67 that are under construction at this point in time. And 160 are planned. U.S. One basically listed last year. But the key is Asia. That is where most of your action is with regard to nuclear power. Now I'll tell you something.
Bob?
Yeah, more.
Just one of the things that I guess is disturbing in the nuclear power industry is, especially in the United States, I mean, you know, we had the nuclear renaissance activities that were going on, and then we figured out all this natural gas we have now, and how interrelated the energy market is, that you've got very cheap natural gas now, which is in the U.S., because of those low prices and switching to capacity there. You've got all these construction plans that used to be on the board have now been taken off the board just because of the economic models that the utilities are using, which are shorter term in nature based off of current energy prices. And it's devastating to the overall U.S. energy policy for the long term, 30, 60 years out, for which you would have nuclear reactors operating.
Yeah, you're dead on. That's exactly right, because what you're looking at is you're looking at natural gas supply today, you're looking at fossil fuels today, where you can be 30 or 60 years. That's why you need an energy policy. That's the challenge. As I said, it goes back to economics. Right now, economics, natural gas is very cheap. That's really hurt the nuclear industry and the ability to build reactors here in the U.S. Again, we talked about how they're fueled basically with enriched uranium, and essentially one neutron will hit a uranium atom, and on average will fission to about 2.5 neutrons. We'll show that here. We talked about the fuel elements. You can see over here the pellets that are located in elements. A fuel assembly will contain anywhere from about 65 to 200 fuel elements, depending on whether it's a light water reactor or a boiling water reactor. But they all basically essentially work the same. Phil talked about the SMRs. I'm not going to go through this other than there was question marks, so somebody had a question on enrichment. And this one thing this does is this shows you the difference in the various designs with regard to the fuels that they use. So the B&W and Westinghouse use LEU fuels, Holtec can use MOX. General Atomics, he talked about using some kind of depleted uranium or spent fuel. Hyperion does use the essentially the reactor grade, research reactor grade fuel up to 20%. And GE and 5G there is supposed to. How does a reactor work? Very simple. Basically, you have the nuclear reactor, which this is a boiling water reactor, generates steam, drives the turbine, drives the generator, sets electricity, and then the water gets circulated back. This is primary fuel. How long does it take for a fission to take place? This is takes one shake. Seriously, believe it or not, that is the technical term. It's about 10 nanoseconds, and for a fission to take place, it's about 100th of a microsecond, and that the technical term for that is. And this just shows you the process of fission. And then if you have a lot of 235 around, that's when you get the but In nature, it only contains 0.7%, so you don't have to worry about a reactor out in nature like that, getting into a situation where you have an explosion taking place. And we design reactors with low. So let's talk about what goes on in the reactor and what to do with the materials left over. So all reactors produce some different radioisotopes. You hear the term transmutation. And you will see a wide range of fission products and materials that come out of reactors. They can produce several kilograms of plutonium-239. There may be only 1 microgram of plutonium-236. Fission products can be stable, such as samarium. You can have half-lives, long half-lives. Technetium has a half-life of 213,000 years. That means half the material is still left after 200,000 years. Cesium, we have 30-year cesium, or different isotopes of cesium is 1 second. So these are various things that are produced in a reactor. Sometimes some of the production things are very valuable that can be used for medical isotopes. In the U.S., the future question is what happens to the fuel cycle in the U.S. in the future? As I said, I showed you before was where we are currently. Currently is a once-through cycle. But there was work that was done previously. If you look at also other countries in the world, they have what's called fuel reprocessing, fuel processing of fuels. So this diagram basically shows you go back to our original uranium mine, goes to refining plant, conversion plant, goes into enrichment plant, and goes to fuel fabricator, and then to power. The one step that's missing in the U.S. to close that fuel cycle is what's called a reprocessing plant or processing plant. And there are several options, as I said. Right now, here in the U.S., basically you have a once-through fuel cycle. No reprocessing. You can partially reprocess the material, and that's some things that we're looking at right now. Where you, basically what you're doing is you're reducing the volume of waste that you have, or you can do full reprocessing, and that would further reduce the volume. All these things are part of the decisions that when you think about nuclear fuel cycle, you have to close that fuel cycle. You have to decide what you're going to do with the waste, how you're going to handle it. So this talks a little bit about how much waste is generated. 95.6% of the fuel that comes out of it still contains uranium, basically uranium fuel. And the assay there is about 0.8%. The other 5% contains 2.9% are your stable fission isotopes. Plutonium is 5%, technetium is about 10%. Minor activities. Most of that heat will decay in about 300 years. In fact, I think over 90% of it decays in about 40 years. So about 5% of the energy value is used in a once-through cycle. So that's another reason we want to have reprocessing or have some way to reuse the fuel, whether it's in a box or whatever, because you're throwing away a large amount of the energy that you have. So why do you recover them? What can you use? Obviously, plutonium has value, and the acidity, energy, and then recycle. And you want to be able to manage the waste. And if you can reduce the waste, again, it gets in economics, how much money you're spending to pay to store the waste. Where do you store the waste here in the U.S.? Last I heard, you haven't found one of them. Challenges that we have.
Hey, Bob, on reprocessing, Europeans reprocess their spent fuel for years. Is it in the U.S., is it a technical reason or a political reason you think that we don't? Political.
I started my career in 1974 working on the processing for the liquid metal fast-breeder reactors. We were building a processor to do krypton and xenon for off gas. All the steps are there. I mean, it's just if somebody wants to know something different, it's political.
Is the politics, Bob, driven by, we just didn't have a lack of champion to communicate? I mean, it's probably a list of reasons, but if there's a top couple that drives those politics.
That goes back to 3 Mile Island.
That's what I thought.
Yeah, I mean, that's about the time that, you know, the reprocessing program was very strong in Berlin, and 3 Mile Island came, a whole nuclear industry. So,
That is nuclear corporation. I mean, that's two stars, something or something. But, you know, I'll just make a comment that it's politics heavily, but they're according to how you factor the economics. You know, for the Europeans and others, the economies there, you just look at the cost of making the fuel versus, you know, once-litre fuel. It's higher, but if you make sure to put in the disposal cost and do the discount off that, and it fits in the economics as well. But yeah, in the U.S., it's all good.
So we talk about just kind of simple picture reprocessing. Again, you reprocess, you got your uranium, you send that back to the reactors. Plutonium mixed oxide, you go back to reactors, and then you got it waste. So the challenge we have in the future, you have reliable energy supply, certainly is the cornerstone of growth, prosperity. And if you look at all the studies that were done, I know I think in the 80s I took a class over UT on energy management and talked about that a country's gross domestic product is directly proportional to the amount of energy that country is generating every year. And if you look at that, I mean, it's a surprising correlation to that. And so I think the last slide I have here talks a little bit about what the demand is going to be here. So that the world population between now and 2050 will continue to grow by about 50%. The energy per capita use will grow by about 30 to 40%, and therefore the world demand is going to grow more than double when you multiply those together. So the challenge is, how do you provide that energy to the consumers so that they can continue to progress? And it is very proportional to it. And our belief is the only source to do that is to keep energy, be able to meet the quantities that are required. That's it.
Got one. You talked a little bit about the fuel chemistry, black art. Is there a research science opportunity, or is everyone just happy with the way they're doing it and they really don't want any help?
It's if you go to the fuel fabricators, you know, around the world, here in the U.S. or whatever, it's kind of like Coca-Cola. They will not let you know the recipe, and they will, to get into their business, and they are very, very protective of that. What they know is that their product, and the utilities know their product will burn however long they want to burn, and they don't want anybody messing with it.
But is there some scientific basis for that? Do they, you know, can someone say, you know, with these additives it ought to burn?
I'm not an expert at fuel fabrication. I'll tell you this, is that the sintering process, you know, how they make the uranium oxide fuel pellets is they make it in oxide and they sinter it, and it gives them the right heat controls, and I'm sure they're continually working on those. I mean, if there's somebody here that knows the fuel fabrication industry, it's been years since I've been in it, and I'm sure they're continuing to develop to get more efficient, you know, their fuel pellets, et cetera, but I'd say it's a hard nut to crack to get into their business. And I do know, because I visited every fuel fabrication facility in the free world back in the 80s, and they were very, very protective.
As you look at component supply to your plant, have other countries imposed peaceful use restrictions or consent rights on if we accept foreign parts?
Yes. With each country, when you do business, particularly when you're working in a classified industry, you have to set up, you have to be concerned about export control. And so you get an export control arrangement with those countries, and so you develop requirements. Some countries require peaceful use restrictions, so we cannot use it for non-peaceful uses. We have an arrangement for some countries for that and some materials that we use. And then, as I said, by treaty, because of those, you can't use that for maybe materials that we go into.
So you see a path to being able to use American centrifuge technology to make trade?
Absolutely. Absolutely. We're not concerned. We don't have any restrictions on us right now that would affect that.
Has it impacted your ability to be as efficient and competitive as possible to preserve that capability?
No, I think what we would prefer is if the U.S. industry would develop, capabilities, manufacturing industry, which we're trying to do it so that we can do it here and be more competitive, but it has not impacted our ability from an economic standpoint. Where we use foreign suppliers, they're like in the feed and withdrawal area, and it's not affecting the centrifuge machines.
Bob, are you anticipating the centrifuge design to change as you start supplying centrifuges to Piketon in the future, or is it going to stay the same?
What do you call the design change?
Well, I don't know, improvements. That's improvements, or, anything that would precipitate.
As I said before, we are on the very beginning basis of what the centrifuge machine can do. You look at the development curve, it comes up and comes over. We're about here. We've identified numerous projects where we know that we can reduce the cost of the machine, improve the reliability of the machine, or improve the fluid output that we would like to continue to do. I told my board of directors, because a lot of people say, you already have a centrifuge machine. Why spend any money on technology? Why do anything in technology? Because you already have a machine, just go run that machine. And I told my board of directors, shoot me in the head if I cannot justify my existence by the return on investment that you put to me. And because our analysis tells us if we do the things that we say we're going to do, and we feel very comfortable through our models that we can do, that we can more than pay for ourselves.
I was wondering, you're not in just a straight manufacturing mode. Okay.
In fact, my job, I'm technology and process engineering, my job is totally development. The way that USEC is set up, we have basically 4 major functions. We have technology, which is the technology process engineering. We have manufacturing, which is a joint venture between us and BMW. We have operations, which is up in Piketon. We have EPC, which is engineering, procurement, construction. They build the plant. So my customers, I'm the design authority for the plant. I provide the design to manufacturing. I provide operations, what the machine will run under what conditions. And then we're providing a special feed withdrawal equipment, et cetera, to EPC for the plant. So each one of those are not customers.
I see. Thank you.